My name is Micah. I'm here today to talk to you about streaming SQL, both what does that mean, how do we apply SQL to unbounded infinite streams, and also why. Why do we apply SQL to unbounded streams? And more generally, why every time we have a new data problem does the answer end up being SQL, even though we all kind of hate it? So let's get started. I'm going to give you a little overview of what we're talking about today. Start talking about kind of the history of query languages and that inexorable trend towards SQL for every data problem. We'll talk about kind of the math behind SQL, how we can apply some of that math and create some new semantics that let us apply SQL to these unbounded streams. And then I'm going to conclude with that kind of polemic, like why is SQL the right answer, even though we hate it. So yeah, let's get started. So I'll give you a little background on myself. I've been doing streaming stuff for essentially my whole career. I started out in ad tech, trying to make like a very batch-oriented data company do streaming stuff, even when we were using Storm, very early streaming technology. Didn't work that well. Then I spent some time doing streaming for fraud detection, and then eventually transitioned fully into a streaming role, leading the Flink teams at Lyft and Splunk. And then most recently, I have co-founded a company called Arroyo to bring streaming to everyone. And I'm not going to give you the whole rundown because this is a vendor-neutral conference here. But basically at Arroyo, we're building a new stream processing engine. We aim to be dramatically easier to operate and easier to program than Flink, as well as being considerably faster. We're written in Rust. It's very cool. Please check out our repo. Okay, and happy to talk more about that later with folks. So to start things off, just want to give you like a little guided tour of how people have been thinking about querying data across kind of a variety of paradigms over the last 50 years. And things really kind of kick off the 60s. We start having actual computers with like whole megabytes of disk. We start immediately wanting to store data and query it. The initial attempts were not that great. We have these kind of like hierarchical query languages on top of like IBM 360s, like massive mainframes with giant tape drives. Pretty quickly though, this guy, Cod, comes up with this idea for the relational model. This paper was in 1970. From there, we get ANSI SQL in 1986. And in between, a bunch of early databases were built around the relational model and around SQL. And that kind of becomes the standard for this for quite a long time. But we're data people, we get bored easily. We want to use new technologies. In the 2000s, that was like graph databases and these specialized graph query languages. And then also for some reason, XML. That was just a thing we did in the 2000s. We wanted to write our queries in XML as well. So this language is like XQuery. From there, we got kind of in the more big data space. We started having like terabytes and petabytes of data, and we started building these like distributed key value stores that couldn't really support relational data or transactional semantics. And we started building these domain-specific languages like Cassandra query language, the MongoDB query language, which were specialized to exactly how the database worked. But then we found out that that's really hard. Most users don't want to become experts in like a particular database that they're querying. And so we're back to SQL. And now all of the new distributed databases are really SQL first and designed around the same relational semantics and transactional semantics as like the original databases. If you look at like the big data or like analytical space, it's kind of like the exact same progression. We start with very specialized tools like MapReduce, where we were writing these giant, for those of you who are a little younger, this is how we used to do big data. We write all this Java code, all these files. And from there, we got kind of like tools to generate MapReduce pipelines with a little bit less code. So I'm particularly a fan of this language here called Sawzall. Like literally no one else in the world loves Sawzall, but it was an early Google approach at this. And we had an open source project called Piglatin that was sort of the same idea. So now we're writing like these high-level programs that get generated into MapReduce. From there, we got kind of these data frame APIs that just vastly reduced the amount of code you had to accomplish these data processing tasks, and were tied to more flexible execution engines that could do more things than just map and reduce. But ultimately, you know how this goes. The specialized APIs have really given way in all of these systems to SQL. And now every system, whether it's Spark or Snowflake, BigQuery, all the new big data systems are once again SQL first. And then in streaming, in MySpace, it's really, you probably can guess the exact same progression here. We start with these very specialized languages. This is the 90s, the big thing was complex event processing, which this was a DSL for that from the 90s. Then we get to like kind of manual graph construction APIs where we're very tied to exactly how these things are executing. This is an example of Storm, which is an early streaming technology. And then from there, we get these higher level data stream APIs, very similar to like the Spark style data frame APIs. But then here we are in the 2020s and we're back. We're back to SQL. Always the inevitable answer. So yeah, it's always SQL. That's just how it goes. But in this particular domain, in streaming, we really have some problems, which is that SQL is fundamentally a batch-oriented query language. And so we need to kind of rethink some of the fundamentals in order to be able to apply it to unbounded streaming data. So before we get into that, I'm going to talk a little bit about, well, what are those mathematical fundamentals of SQL? And in this talk, I'm also going to talk a lot about semantics, which is a big math word that just means like a precise description of how some language concept works. So it's just a way for us to talk precisely about the behavior of our programs. So SQL, as I mentioned earlier, it's based on this mathematical concept called relational algebra. This came out of the original relational algebra paper from 1970 from Edgar Codd. And in algebra, for those of you who did not do university math, is just like a set of formalized operations on a particular class of sets. So in relational algebra, that class of sets is called a relation, which you probably better know by the kind of industry term table. So these are just like ways of formally defining operations on tables. Relational algebra describes some kind of set operations that are pretty common, like set union, intersection, difference, as well as some specialized relational operations like selection, which is the SQL where clause, projection, which is like the SQL select clause, and joins, as well as ways of aggregating over multiple elements in these sets. So these are like your aggregate functions, sum, count, average, etc. To make that a little bit more concrete, I'm going to go through some examples here. So here's some tables we're going to be talking about. This orders table that just has transactions for a particular, like a e-commerce store or something. We have page views, users browsing around this website. So we can look at some simple queries we all probably understand. Hopefully everyone here has done at least a little bit of SQL. So here we're going to just compute like a tax-inclusive price from our orders table with a where clause that filters out certain records. If we look at how like the semantics of this query work on a batch data set, it's pretty straightforward. We have our data set. We're going to go like row by row. We're going to check if things match our filter, our where clause. And then we're going to project out the particular calculation we're trying to make, this price times 1.08. And that's pretty straightforward. We can also do aggregates. We can do things that kind of combine multiple rows. So here we're going to count the number of rows that match a certain condition. And in our batch case, again, this is like pretty straightforward. We go through each of our rows. We kind of select out the ones that match our condition. And then we project out our aggregate by summing all the rows that match. So that's the batch case. But how do we apply this to streaming? We take that first query, we basically want to create a mapping from kind of those concepts, those relational algebra operations and sets, into a new paradigm where we're talking about like unbounded data, so data that never ends. And the first thing we can do is take the table and create a new mathematical object that we'll call a stream. And a stream is very similar to a table. You can see the definition looks exactly the same, except I've said stream instead of table. But unlike a table, a stream is unbounded. That means that we never have a complete view of the data. We can always get more records at any time. If we try to kind of apply our same semantics onto a stream, sometimes that works. So here's the kind of tax calculation example. And if we see how this executes on a stream, we kind of get in each row. We can filter out those rows. And then we can project out the column that we need for our computation, this price column, and return the result. And actually, this works totally fine. We can do exactly the same operations we did in the batch case. We don't need to really introduce any new ideas. But if we look at that aggregate query we did, the count star, we actually start to run into some problems just blindly applying relational algebra to streams. So if we look at how this applies in a stream, we are doing the same selection, so doing this where clause, filtering out rows, but we never are quite able to do this aggregate, right? Every time we see a row that matches, we produce this one that we're going to count, but we just keep getting more rows. We never get to the end. We're never able to produce that final count. And so if we want to make this work, we're actually going to need some new semantics. We're going to need a way to actually answer questions about multiple rows without ever having all of the rows. And there's kind of two ways that people have gone about this, or two ways I'm going to talk about, ways of extending relational algebra with streaming semantics. And I'm going to talk about two of them here. The first one I'm talking about I call data flow semantics because it came out of this paper, the data flow model, a practical approach to balancing correctness, latency, and cost in massive scale, unbounded, out-of-order data processing. This is a very influential paper from Google that really laid out their philosophy around streaming data based on a lot of kind of different systems that they had built over the years. The kind of core insight of this paper was that in streaming systems, we have a really fundamental concept of time, right? In normal databases, the rows are just laid out however, according to the index or however the data is queried or inserted. But in streams, they tend to come in basically in time order. Not completely, but like more or less in time order. And we can actually exploit that to do a lot of kind of time-oriented queries that people are often interested in doing in streaming. So in streaming, we often talk about kind of windows that divide time up into discrete chunks. There's sort of three standard ones. There's tumbling windows, which are fixed-sized and non-overlapping, sliding windows, which are fixed-sized and overlapping, and session windows, which are defined by like a minimum gap size. And if we try to like just use those windows directly in SQL, we still have this kind of problem of not having any bound on our data. So this is like sort of how you would do a tumbling window in standard SQL, truncate the minute and group by that. And in our, as we saw before, like with these aggregates, group bys, whatever, they never finish because the group by has to wait for all of the data. But since we know that actually our stream is time ordered, more or less, we can exploit that to basically enable our tumbling window to complete once we've sort of seen all the data for that window. There's different ways this idea gets expressed in different streaming SQL dialects. This is an example of Arroyo SQL, which is also quite similar to Flink SQL. And here we've basically replaced that standard SQL date trunk with a specialized streaming UDF called tumble. And what this does is instruct the streaming system that we're opting into time-oriented semantics, or data flow semantics, and that once the streaming system thinks we've seen all the data for this window, for this minute, it's going to be able to compute the aggregate over that minute and produce the result. So we look at how this actually executes. We have our stream here again, it's infinite, but for every minute, the streaming system is able to say, okay, I know you're doing a time-oriented query. I know you're dividing time up in this particular way. And as a result, once we get to the end of that minute, once the system knows we've seen all the data, it is able to emit that result. And we've built up kind of semantics that can actually produce outputs. But we do have a problem here, which is that in the perfect world, events come in exactly in order. But in the real world, they do not. I used to work at Lyft on a lot of data that came from mobile phones, which have a bad habit of like going into tunnels or just being turned off or running out of battery. And you can get data from those phones minutes or hours or days later. So we can't just like blindly assume that like once we've seen data for a particular time, that we've actually seen all the data up to that point. We're not able to just naively use like a wall clock to decide if these windows can be computed. And in order to think about this problem, the data flow model introduces this idea of event time versus processing time. So event time is like the logical time that an event occurred in the real world. So on my app, it's when I push that button, according to the local phone clock, which may also not be that accurate to the real world, but that's what we have. And then processing time is when we actually go to deal with the data. It's when we actually ingest it into our streaming system. Ideally, there's this like diagonal line here in this graph. So there's a kind of straightforward relationship between event time and processing time. But in reality, events are going to be delayed or misordered. And that's this red line here. Sometimes we have to wait, and there's more of a gap between event time and processing time. So in order to deal with this, the data flow paper introduced a concept called a watermark. So a watermark is a lower bound on event times that we expect to see in the future. What this means is if we have a watermark for 12:01 p.m., then we do not expect to get any data from before 12:01 p.m. And what that does is let us compute our windows. Now we can close and compute any window that expires before 12:01. Then we have the question, how do we compute the watermark? Ideally, it would just be that exact line I showed before. It's exactly how much each of our events is going to be delayed or reordered. But in practice, we have no real way of knowing that. So we have to estimate it somehow. And that estimate is, it should ideally be on the left side of this line, right? We should expect to wait longer than the ideal for these events to arrive. But sometimes we're going to get wrong. And when that happens, we'll have closed our windows before we get the data that was supposed to go into that window. And this is called late data. Different systems have different ways of handling it, but most SQL systems will just drop that late data. And then in terms of how you actually produce this estimate, there's a lot of different techniques of differing levels of sophistication. The most simple one is you just have a fixed offset from the last time you've seen. So if we've got an event from 12:01, maybe we assume we've seen all the events from 12 p.m. And you can kind of adjust that bound based on what you know about your data. So if you know all your data typically comes in within a second, you can make that tighter. And then there's like statistical techniques. This paper had some cool ones where you are trying to estimate completeness. You can essentially think of this as a slider between latency and completeness. So if you're willing to deal with less complete data, you can get data faster. If you're willing to deal with more complete, or if you need more complete data, doing financial stuff or whatever, you're going to wait longer in order to get to ensure that you've seen all of the data. And we talked about windows. The same idea works for joins as well. So normally joins have the same problem that in order to produce the join in relational algebra, you have to have all of the data. You have to produce all of the matches between the left and right side, according to the particular join semantics. But if we put this on a time-oriented window, then we can compute it there, and we can just produce the outputs within that time frame driven by the watermark behavior. Cool. So that was kind of the earlier idea that people had about how to solve this problem, applying SQL to streaming data. This is implemented in a bunch of systems, including Flink, Arroyo. Some newer systems have started adopting this as well. But it's not the only way people have gone about this. A kind of newer approach to this problem is something I'm going to call update semantics or materialized view semantics. So the idea here, we can go back to like our initial query that we couldn't compute, our basically tumbling window with standard SQL with an aggregate. And we basically just give up the idea of absolutely computing this, of getting an actual correct result for this query. Instead, we reframe the problem as incrementally converging to the correct result. So you can imagine at the end of time, we'll have seen all of the data, and we will be able to produce exactly the right value for each one of these windows. But at any given time, we've only seen some of the data. So every time we get a new record, we just incrementally improve our result to get closer to that final value. So here's an example of that query. In update semantics, we get a row of data. And then we're going to, and just to remind you, this query is doing a sum of sales over an hour tumbling window grouped by store ID. So the first time we see a store ID, we're going to create a row, or a store ID in an hour. We're going to create a row with that value. When we see another store ID, we're going to create another row for that store ID an hour. And then when we get a new record for a store ID and hour that we've already seen, we're going to update the existing value in our database with that new data. So you can see as we get in all the data for this hour, it slowly converges to the correct result. And this is nice. Oh, got a little out of order. And this is nice because we can support essentially any SQL query in this fashion, right? We can always incrementally converge towards the traditional semantic, the traditional relational algebra answer for a query. The downside is that we don't really know when we'll have that answer. The data flow semantics with the watermark gives us like a point in time when you can process the data, where you can drive downstream systems from it. Whereas in like the incremental update approach, it just constantly is converging to the right answer, but we never know when it's going to get there. We also have kind of like a practical problem here, which is that if you look at the semantics of this query, SQL is not time-ordered. This query is not time-ordered, which means we can get data for this hour at any time. Like in a year, we could get data for this hour. And under the semantics of update SQL, we're supposed to always be able to update it at any time. But that means we really have to like keep all of the data for all of time, even when we've long since passed this time period. And so in practice, these systems add a little bit of impurity, add some kind of TTL in order to tell us when we can actually remove data from our state, because otherwise our state just grows unbounded. So this is an example of materialized SQL. They have this special mzNow function that gives you kind of a pointer to the current time that lets you build these TTLs. Other systems like Flink or Arroyo just have an implicit config that controls the TTL. And you basically need these for anything that's stateful over time, so your windows or joins. In terms of systems that kind of implement this, Materialize, I think, was the first to really push this forward as a model, maybe a little ahistorical. Flink also supports this now, Rising Wave, and Arroyo also supports this style of SQL. And then we often want to like consume this in different ways. So some databases will implement their own kind of storage layer. So Materialize, for example, incrementally updates its own state and can serve that directly. Other databases produce a change feed of these updates that can then be applied to like a Postgres or another relational database. This is an example of Debezium JSON, which is a common way that people both feed these systems and also consume them. So for a system like Flink or Arroyo that can produce this output, you can then directly apply this to your transactional database and get a something, essentially a materialized view that you can query to like power your applications, your analytics. And often you see these kind of architectures where you have a transactional database that's producing a change feed, so a record of all of the operations, updates, inserts, deletes, whatever, that gets consumed as a change feed by the streaming engine in this update way. You can then apply arbitrary SQL to that change feed as if it were running on like the original transactional database. And then that produces a new change feed of the outputs of that like materialized view. So we have these two different semantics, two different ways of thinking about streaming SQL. I think there's no right answer to which one you should be using or which one databases should support. They really have different benefits and drawbacks. For data flow semantics, we rely on a watermark to decide when windows are complete. That means that we can lose data if it arrives after the watermark. But on the plus side, it gives us a time that we can actually handle that result. With update semantics, we incrementally converge to the answer, so we can always handle late data up to our TTL. But we never get told by the system, here's when you can actually use this data. So you end up needing really an out-of-band system to decide, like, okay, we've waited long enough for this query to return for this time period. We're able to like act on that time period. Data flow semantics, we can't really define this on every SQL query. We need a way to bound time. So we're almost always having these like time-oriented windows, or some way to bound time in the query. Whereas update semantics, you can define basically any SQL query in these semantics. Materialize have gone extremely deep in that. They support crazy recursive CTEs and all sorts of obscure features that no one, I think, uses. But it's very cool. In terms of like efficiency, the data flow systems tend to be more efficient because we process these windows once the watermark passes, whereas update systems have to do work on every event. And in terms of like how these are used, like the data flow systems are generally more push-driven. So these are powered by, or these power kind of real-time applications, things that need to take action on the world. For example, a fraud system that needs to tell you to like cancel a transaction or ban a user. And the update systems are often used for more analytical use cases or things that are more poll-driven, where you're querying the state of the table. And just some example use cases I've seen in my career for these two approaches. But a good streaming system doesn't make you choose. So a system like Flink or Arroyo supports both of these, and you can even like mix and match them. You have parts of your query that are watermark driven and parts that are incremental. Cool, so we've covered how streaming SQL. So let's talk about why. Why, as we covered in the beginning, like why do we always end up at SQL? Every new way we want to process data, it's always SQL. I mean, one of those reasons is just SQL is unkillable. It is the zombie of programming languages. We've been using it for 50 years. It's going to be here in 50 years from now. No matter how many times people try to kill it, it just keeps coming back from the dead. But I think there actually are some good reasons of this. And I say this as kind of a SQL hater who's come around building now a SQL engine. And some of these perspectives actually come from being a SQL engine designer and seeing how SQL actually makes my job easier. One of those things is that SQL is fundamentally a declarative language. It doesn't tell you how to compute a result. It tells you what result to compute. And that's nice for users in a lot of ways, because you just have to think about the end result. You don't have to think about the algorithm. You don't have to know about a hash join. You don't have to understand the database technology that's going to give you your result. But it's also really nice as a designer, because it gives us a lot of flexibility in how we actually implement these things. So just to walk through an example here, here's an example of like Flink data stream API. This API really is describing a graph. This is that graph. And it is exactly defining this graph. So when we execute it, we really do need to actually execute this graph at runtime. We have, in this case, a source that we're reading from. We do a filter. We do a window with a shuffle to repartition the data, and then our aggregate. But it turns out this is not actually the efficient way to do this query in general. And if we have a declarative description of the problem, rather than like, here's the graph I want you to execute, we can optimize this into a much more efficient form for execution. So ideally, this is actually what we'd like to do. We'd like to push the predicate into the source, so filter the data when we read it, as opposed to after we've read it. And then we want to split this like count star into a local global aggregate. So basically, being able to compute some of the aggregate on one side of the shuffle before we send all this data around the network, and then the other part after we've already reduced it after the shuffle. But when the user specifies it exactly as the graph, we don't have that flexibility to do these optimizations. And this just keeps getting better for users, right? Like, even if your database can't do all this stuff today, you can use the same SQL, and tomorrow it may be able to do some of these more powerful optimizations. SQL is just also amazingly flexible. This is an IBM 360. This is a machine from 1978, I think. This was like the kind of computer we used to run SQL on when it was first developed. This guy at this teletype machine is like writing punch cards with his SQL queries. And yet we've taken this technology, it's evolved, but not even that much from the punch card days. And we've applied it to all of these different use cases that were probably unimaginable 50 years ago. We have our traditional transactional databases like Postgres and MySQL. We have analytical databases like Pinot and Druid. We have batch processing systems. We have stream processing systems. We have metric databases like Influx. We have graph databases, data lakes. All of these new ways we store and query and access data have proven adaptable. We can apply SQL to all of these different paradigms. And then finally, SQL is incredibly extensible. This is for better and worse, I would say, as an engine designer. There is no language SQL. There are 100 different SQL languages implemented by every different database and data system. But it does mean you can apply the same basic ideas, the same basic semantics and syntax to all these radically different problems. And SQL has proven to have a lot of these like pretty powerful extension points. We're able to add like materialized views, event time, user-defined functions, aggregate functions, add entirely new operators, optimizations, windows. Like, SQL has proven extensible enough to adapt to all of these different cases. And so given that we spent 50 years of writing SQL from IBM mainframes that we programmed with punch cards all the way to modern state-of-the-art OLAP databases and streaming systems, I fully expect like our great-grandchildren are going to be like on the moon, on Mars. They're still going to be writing SQL. We're still going to be processing data this way in 50 years. And I think we should accept it and also really embrace it, that SQL is a technology that empowers, I don't know, maybe not billions, hundreds of millions of people across the world to use data and to get value from all of these systems. So thank you.